Imagine waking up one morning and realizing that you don't know where you are. If you were a sailor on the open seas, you'd know the feeling. You go to bed at night, and while you're sleeping, your boat drifts on the sea. But how far? And in which direction? With no directions, no signs, no one to point the way, how in the world do people figure out where in the world they're going? How do you discover where you are, and how do you find your way home?
You know, that's the same problem that faced our ancestors when they began exploring the world. There they were, eager to sail off and find out what lay beyond the horizon, but they still wanted to be able to get back to the ports they left behind.
For centuries, leaving home was dangerous business. People couldn't be sure they could find their way back.
As long as they stuck close to shore, they could use landmarks to find where they were. For instance, sail north until you hit the big peninsula, then head into the setting sun. They could even draw maps and show others how to repeat the journey. But once they sailed out of sight of land, they faced a serious problem. No landmarks, no signposts, nothing in any direction except for water. If explorers were truly going to explore, they couldn't always stick close to shore. If they really wanted to go out and find someplace new, they had to figure out how to find their way without using landmarks. So they looked to the sky.
Our ancestors spent a lot of time watching the sky. They figured out that some things about the sky were pretty dependable.
The sun, for instance. It rises every morning in the east and sets each night in the west. You can count on it. And once you know that, you can use it to give you a rough idea of the direction you're headed. For example, you head into the sun in the morning as you go out to sea. The sun rises, goes through its cycle, and sets behind you in the west. When you want to return home at the end of the day, you just turn around and head straight towards the setting sun.
The early Polynesians were one group who had to be good at using the sky to find their way. Their island homes were scattered far across the South Pacific, with vast expanses of ocean in between. Traveling for days out on the open sea, Polynesian sailors could and did get lost. They could set rough courses by the sun, but what if they were still far from home when the sun went down? Like sailors elsewhere, the Polynesians learned that the night sky also had signposts, the moon and the stars. On a clear night, the stars in the sky seemed to turn like a wheel spinning around a fixed point. Early Polynesians used that wheel to help them find their way.
This is a Marae temple.
Like many ancient peoples, the Polynesians navigated by a combination of mysticism, experience, and plain luck. This stone structure, called a morai, was both a temple and a guide for traveling over the sea.
Width of the ocean canoes also.
So this is the same size and shape of the canoes that you use to travel around?
The same size with the all ocean canoes.
Oh. And what was this used for?
This was the hub of the Polynesian navigation system. Mm-hmm. Yeah, they always go out from here and come back here to any place of the Polynesian Triangle.
You always had to start from this spot?
Always, always.
And why was that?
Suppose you want to go to Hawaii. From the hub, the seer, who was the captain, sent his spirit to destination. Then the expedition from here go out to the
Polynesian seers, or navigators, paid careful attention to the world around them. They were believed to have magical powers, but they also knew a lot about the relationships of land, sea, and sky. They could use the sun and other stars to find their way from island to island, but they could also lose their way if clouds or stormy weather blocked their view.
And tell to the guys steering now, you see that star? You go straight toward it.
Before people could really explore the world and make maps good enough so others could follow them, they had to find a better way of understanding where they were.
The first step, the key to figuring out your precise position, is to use something that's already known. For example, say there's a lighthouse on this island, and over here there's a prominent point of land. Now I'm on a ship somewhere out here, and I need to know exactly where I am so I don't run into any dangerous reefs or rocks along my path. Now the first thing I do is I take my compass and I find the direction to the lighthouse. I can draw a line on my chart representing the heading from the lighthouse to me. The next thing I do is I take my compass again and find the direction to the prominent point of land. I draw my line, and where they intersect, there I am.
But how do you chart your position far at sea, where no landmarks exist?
As early as the 2nd century BC, the Greeks figured out that if you laid a grid of perpendicular lines over a map and then numbered them, you could use that grid to pinpoint places all over the globe. The grid provided a nearly infinite number of known locations around the world. The Greeks could then use those known locations to plot their precise position. So all you need is a map with a grid, and you can find anything you want, right? Well, not quite. See, there's one big problem. Maps are flat, and our world is round, kind of like this coconut. And it's really hard to make a flat map describe something round, like the Earth.
Once early map makers discovered that the world was round, they had to come up with a grid-like system to fit our spherical world. The early Greeks drew maps with lines running east and west, lines that make huge circles, like belts around the planet. They called those lines parallels because they never touch. Parallels measure latitude, how far north or south a place is. The map makers drew another set of lines from north to south, crossing at the poles and continuing on around the globe. These lines are called meridians, and they measure longitude, how far a place is toward the east or west. Before latitude and longitude could serve as reference points, they had to be named or numbered, so people would know where they were measuring from. It was relatively easy to choose a starting point for latitude. The Greeks put it around the middle of the Earth, halfway between the North and South poles. They called it the equator and gave it the number 0. Choosing a starting point for longitude was trickier. The Earth doesn't have east and west poles, so there's no real reason to put 0 along any particular meridian. For years, the location of the 0 or prime meridian depended on which country was making the map. After long debate, most nations agreed in 1884 that the prime meridian, 0 longitude, would run through Greenwich, England, just outside of London. The grid of latitude and longitude was a great idea, but it would take centuries before people came up with reliable ways to calculate their exact positions on that grid. At the Royal Observatory outside London, the British spent nearly 200 years looking for better ways to determine latitude and longitude. The observatory still exists at Greenwich, right on top of the prime meridian. Here, visitors can learn just how hard it was for our seafaring ancestors to calculate their positions. Latitude is relatively easy to figure. All we have to do is look to the sky. From anywhere north of the equator, the North Star, Polaris, is ideally located just above the North Pole. It's fairly easy to measure the star's height in degrees above the horizon. That angle is the same as the degree of latitude. If the angle between Polaris and the horizon is 30 degrees, for instance, you know you're on the 30th parallel, 30 degrees north latitude.
Longitude is a little harder to figure out. Instead of angles, longitude is based on time. Now remember that the lines of latitude and longitude are really circles going all the way around the globe. and there are 360 degrees in a circle. Also, the Earth is spinning, one complete rotation every 24 hours, which makes a day. Now, if you divide 360 degrees by 24 hours, you get 15. The Earth turns 15 degrees over the course of an hour. So if you know what time it is where you are, and what time it is back here at the zero longitude, you can use simple arithmetic to figure out how far east or west you are of the prime meridian. But first, you have to know what time it is back in Greenwich.
The quest for an accurate timepiece was especially urgent to the British, who had suffered terrible shipwrecks. In 1707, an entire British fleet bound homeward from Gibraltar ran aground, killing 2,000 men. It happened because the admiral in charge of the fleet had no idea where he was. An obscure English carpenter, John Harrison, gets credit for inventing the first accurate seafaring clock, or chronometer. Most early clocks ran on pendulums, which kept fairly accurate time on dry land. But tossing waves and damp sea air unbalanced their mechanisms, making them run too fast or slow. Harrison came up with a whole new kind of clock.
So tell me how this clock solved the problems dealing with the ship's motion and the pendulum getting all messed up.
Right, well, instead of a pendulum, what Harrison fitted here are two bar balancers, which are interconnected at their centers with ribbons, and they move in anti-phase from one another, so that any effect of motion on one balance is directly counteracted by the same effect on the other one. It works really well, and you can take hold of this machine and gradually move it around, and while it's running, it just doesn't seem to notice that it's being moved at all. Harrison went on to make two other large machines, but they never performed accurately enough. And it was only 30 years after he started this project that he realized finally that the solution lay in developing watch technology, not in clock technology. And with this watch, his fourth timekeeper, he eventually incorporated a balance which has high energy stored in it by increasing its frequency. And it was this watch, really, that was the first practical marine chronometer. And it was the development on this machine which eventually gave sailors across the world the longitude that they needed at sea.
Today's mariners still navigate by latitude and longitude, just as their forebears have for hundreds of years. But the tools they use to do the job are far more accurate than those the old sailors used. And for huge ships like the QE2, steering an accurate course is important indeed.
In a few moments, we'll be setting sail across the Atlantic Ocean, all the way from England to New York City. It's a 5-day voyage on board the luxury liner, the Queen Elizabeth II. The QE2 is a lot more sophisticated than the old sailing ships of the 18th century, but she still uses latitude and longitude to find her way across the sea.
Up to us. Slow ahead, 2 engines. Queen Elizabeth II, we should be making a lake turtle.
Coming up to a beam of fuel kicker there from Carroll and chopping over to 11 with QE7.
Sailing clear across the North Atlantic, a 5-day journey through sometimes rough and icy seas, was terribly dangerous before inventors came up with the tools that keep modern navigators on course.
Now, this device is called a sextant, correct?
That's right.
Okay. It looks really complicated. How does it work? And why do you use this?
The sextant actually is the second most important piece of navigational equipment that the old sailors had. When this machine instrument was developed about the same time as the marine chronometer, and linking the sextant with a chronometer, they were able to navigate around the world with safety. The sextant, in fact, is an instrument to measure the altitude or the angle of a heavenly body above the horizon. This we do quite simply. If you look at the instrument itself, there's a plane reflecting mirror just there, and here is a glass which is split. There's a mirror on one side and a plain glass on the other. These are shades for the sun, we don't bother with those at the moment, and a telescope. And your intent when you're using this is that you move this to a certain position so that you get a reflection in this mirror here of whatever you're looking for, sun, moon, or stars. That is reflected down into that mirror and into your eye.
Okay.
At the same time, you've got the horizon showing through the plain glass. And by adjusting this arm, you can actually make sun, moon, or stars just kiss the horizon. And you measure the angular height, the degrees it's above the horizon, that kind of thing.
Okay. How do you figure out your latitude and your longitude?
Okay, historically, that was done by reference to a celestial body, either the sun or the stars. And
Today's navigators still look to the sky to chart their courses. But instead of referring to the sun and the other stars, they can find their position instantly, in good weather or bad, by referring to man-made satellites orbiting the Earth.
the longitude. Now we have a series of satellites which have been put around the world into stationary positions, geostationary orbits, and those we use instead of the sun or the star. We have a satellite receiver here called a Global Positioning Satellite Navigator.
Okay.
And it will measure our position in relation to those satellites that are around us, usually using up to 4 satellites at any one time to give a very accurate position to within 30 meters.
30 meters.
On long voyages across the open sea, a single degree off course can send a ship far from its destination. But with increasingly sophisticated means of measuring latitude and longitude, modern-day navigators have little trouble getting precisely where they want to go. Latitude and longitude were designed to help sailors. Even the word navigate comes from Latin words meaning to drive a ship. But sailors aren't the only ones who need to know exactly where they are. Increasingly sophisticated navigation devices can also help us find our way over land and in the air.
This is one of the brand new 737-400s, right?
Right.
I've always wondered, when you're in a plane and you're flying from place to place, you're surrounded by air and you don't really have any landmarks. So how do you figure out your position?
The whole system is based on latitude and longitude. It starts out, when we start our system in the morning, it asks us where we are. So we have a flight management computer system and we have an inertial reference system. And they integrate into each other. When we start them up in the morning, it says, when we're at the gate, it says, where are we? And so we set our inertial reference system position, latitude and longitude, into the system. The inertial reference system has gyros. So as we get pushed back from the gate and as we start taxiing, it senses and it feels all of our movement, both forward and aft. So as we roll down the runway, it feels the acceleration of the jet accelerating. And as we lift off at about 160 miles an hour, it knows that we're at 160 miles an hour and that we're going southbound. So when we go to like San Francisco, we want to go to the end of the runway at San Francisco, we program that in, and then we go up and punch our autopilot to lateral navigation, and it will take us right directly to the end of the runway at San Francisco.
When people travel west across the Pacific, something strange happens. No matter what time of the day or night, when you cross the 180th meridian, one day turns into the next. It all happens at the international dateline, exactly halfway around the world from Greenwich. As the Earth rotates, the dateline sweeps counterclockwise, slowly pushing the old day out and bringing in the new. No matter where on Earth the sun is shining, the dateline separates one day from the next. Time, the stars, latitude and longitude, Navigating the world can seem like a vast and complicated task. But modern-day travelers have a whole array of high-tech tools to help them find their way with pinpoint accuracy. It took centuries to develop the system we call latitude and longitude. Centuries of learning to understand the relationships between our planet and the celestial bodies overhead. From the early Polynesians and their rough sightings of the sky, to high-tech satellites that steer us within meters of our destination, the principles of latitude and longitude have taught us to describe our planet and find our way around it safely and with confidence.